Today on UPSC Science View, progress of mankind over the last 100 years have come at a cost. The warming of the Earth's surface and troposphere, also known as the greenhouse effect. Hello and welcome to UPSC Science View, and today let's learn about the greenhouse gases. Any gas that has the property of absorbing infrared radiation emitted from Earth's surface and re-radiating it back to the Earth's surface, thus contributing to the greenhouse effect, is known as a greenhouse gas. Carbon dioxide, methane, and water vapor are the most important greenhouse gases. To a lesser extent, surface-level ozone, nitrous oxides, and fluorinated gases also trap infrared radiation. Greenhouse gases have a profound effect on the energy budget of the Earth system despite making up only a fraction of all atmospheric gases. Concentration of greenhouse gases have varied substantially during Earth's history, and these variations have driven substantial climate change at a wide range of timescales. In general, greenhouse gas concentrations have been particularly high during warm periods and low during cold periods. A number of processes influence greenhouse gas concentrations. Some, such as tectonic activities, operate at timescales of millions of years, whereas others, such as vegetation, soil, wetland, and ocean sources and sinks, operate at timescales of hundreds to thousands of years. Human activities, especially fossil fuel combustion since the Industrial Revolution, are responsible for steady increases in atmospheric concentrations of various greenhouse gases, especially carbon dioxide, methane, ozone, and chlorofluorocarbons or CFCs. The effect of each greenhouse gas on Earth's climate depends on its chemical nature and its relative concentration in the atmosphere. Some gases have a high capacity for absorbing infrared radiation or occur in significant quantities, whereas others have considerably lower capacities for absorption or occur only in trace amounts. Radiative forcing, as defined by the Intergovernmental Panel on Climate Change (IPCC), is a measure of the influence a given greenhouse gas or other climatic factor, such as solar irradiance or albedo, has on the amount of radiant energy impinging upon Earth's surface. To understand the relative influence of each greenhouse gas, the so-called forcing values, given in watts per square meter, calculated for time period between 1750 and the present day, are used for comparison. Let's take a look at the major greenhouse gases. Water vapor. Water vapor is the most potent greenhouse gas in Earth's atmosphere, but its behavior is fundamentally different from that of the other greenhouse gases. The primary role of water vapor is not as a direct agent of radiative forcing, but rather as a climate feedback, that is, as a response within the climate system that influences the system's continued activity. This distinction arises because the amount of water vapor in the Earth's atmosphere cannot, in general, be directly modified by human behavior, but is instead set by air temperatures. The warmer the surface, the greater the evaporation rate of water from the surface. As a result, increased evaporation leads to a greater concentration of water vapor in the lower atmosphere, capable of absorbing infrared radiation and emitting it back to the surface. The next major greenhouse gas is carbon dioxide. Carbon dioxide, CO2, is the most significant greenhouse gas. Natural sources of atmospheric CO2 include outgassing from volcanoes, the combustion and natural decay of organic matter, and respiration by aerobic, oxygen-using organisms. These sources are balanced, on average, by a set of physical, chemical, or biological processes called sinks that tend to remove CO2 from the atmosphere. Significant natural sinks include terrestrial vegetation, which takes up CO2 during photosynthesis. A number of oceanic processes also act as carbon sinks. One such process, the solubility pump, involves the descent of surface seawater containing the dissolved CO2. Another process, the biological pump, involves the uptake of dissolved CO2 by marine vegetation and phytoplankton living in the upper ocean or by other marine organisms that use CO2 to build skeletons and other structures made of calcium carbonate. As these organisms expire and fall to the ocean floor, their carbon is transported downward and eventually buried at depth. A long-term balance between these natural sources and sinks leads to the background or natural level of CO2 in the atmosphere. In contrast, human activities increase atmospheric CO2 levels primarily through the burning of fossil fuels, that is oil and coal, and secondary natural gas for use in transportation, heating and electricity, and also through the production of cement. Other anthropogenic sources include the burning of forests and the clearing of land. Anthropogenic emissions currently account for the annual release of about 7 gigatons or 7 billion tons of carbon into the atmosphere. Anthropogenic emissions are equal to approximately 3% of the total emissions of CO2 by natural sources, and this amplified carbon load from human activities far exceeds the offsetting capacity of natural sinks. Carbon dioxide has consequently accumulated in the atmosphere at an average rate of 1.4 parts per million or ppm by volume per year between 1959 and 2006, and roughly 2 ppm per year between 2006 and 2018. Overall, this rate of accumulation has been linear, that is, uniform over time. However, certain current sinks such as the oceans could become sources in the future. This may lead to a situation in which the concentration of atmospheric CO2 builds at an exponential rate, that is, at a rate of increase that is also increasing over time. The natural background level of carbon dioxide varies on a timescale of millions of years due to slow changes in outgassing through volcanic activity. For example, roughly 100 million years ago during the Cretaceous period, CO2 concentrations appeared to have been several times higher than today. Over the past 700,000 years, carbon dioxide concentrations have varied over a far smaller range, in association with the same Earth orbital effects linked to the coming and going of the ice ages of the Pleistocene epoch. By the early 21st century, carbon dioxide levels reached 384 ppm, which is approximately 37% above the natural background level of roughly 280 ppm that existed at the beginning of the Industrial Revolution. Atmospheric CO2 levels continued to increase, and by 2018 they had reached 410 ppm. According to ice core measurements, such levels are believed to be the highest in at least 800,000 years, and according to other lines of evidence, may be the highest in at least 5 million years. Radiative forcing caused by carbon dioxide varies in an approximately logarithmic fashion with the concentration of that gas in the atmosphere. The logarithmic relationship occurs as a result of a saturation effect wherein it becomes increasingly difficult as carbon dioxide concentration increase for additional carbon dioxide molecules to further influence the infrared window. The logarithmic relationship predicts that the surface warming potential will rise by roughly the same amount for each doubling of carbon dioxide concentration. At current rates of fossil fuel use, a doubling of CO2 concentrations over pre-industrial levels is expected to take place by the middle of the 21st century. A doubling of CO2 concentrations would represent an increase of roughly 4 watts per square meter of radiative forcing. Given typical estimates of climate sensitivity in the absence of any offsetting factors, this energy increase would lead to a warming of 2 to 5 degrees Celsius over pre-industrial times. The total radiative forcing by anthropogenic carbon dioxide emissions since the beginning of the industrial age is approximately 1.66 watts per square meter. The second most important greenhouse gas is methane, CH4. Methane is more potent than carbon dioxide because the radiative forcing produced per molecule is greater. In addition, the infrared window is less saturated in the range of wavelengths of radiation absorbed by CH4, so more molecules may fill in the region. However, CH4 or methane exists in far lower concentrations than carbon dioxide in the atmosphere, and its concentrations by volume in the atmosphere are generally measured in parts per billion (ppb) rather than ppm or parts per million. CH4 also has a considerably shorter residence time in the atmosphere than CO2, carbon dioxide. Natural sources of methane include tropical and northern wetlands, methane oxidizing bacteria that feed on organic materials consumed by termites, volcanoes, seepage vents of the seafloor in regions rich with organic sediment, and methane hydrates trapped along the continental shelves of the oceans and in polar permafrost. The primary natural sink for methane is the atmosphere itself, as methane reacts readily with the hydroxyl radical OH- within the troposphere to form CO2, carbon dioxide, and water vapor, H2O. When methane reaches the stratosphere, it is destroyed. Another natural sink is soil, where methane is oxidized by bacteria. As with carbon dioxide, human activity is increasing the methane concentration faster than it can be offset by natural sinks. Anthropogenic sources currently account for approximately 70% of total annual emissions, leading to substantial increases in concentration over time. The major anthropogenic sources of atmospheric methane are rice cultivation, livestock farming, the burning of coal and natural gas, the combustion of biomass, and the decomposition of organic matter in landfills. Future trends are particularly difficult to anticipate. This is in part due to an incomplete understanding of the climate feedbacks associated with methane emissions. In addition, as human population grows, it is difficult to predict how possible changes in livestock raising, rice cultivation, and energy use will influence methane emissions. It is believed that a sudden increase in the concentration of methane in the atmosphere was responsible for a warming event that raised average global temperatures by 4 to 8 degrees Celsius over a few thousand years during the so-called Paleocene-Eocene thermal maximum, or PETM. This episode took place roughly 55 million years ago, and the rise in methane appears to have been related to a massive volcanic eruption that interacted with methane-containing flood deposits. As a result, large amounts of gaseous methane were injected into the atmosphere. It is difficult to know precisely how high these concentrations were or how long they persisted. At very high concentrations, residence times of methane in the atmosphere can become much greater than the nominal 10-year residence time that applies today. Nevertheless, it is likely that these concentrations reach several parts per million or ppm during the PETM. Methane concentrations also varied over a smaller range in association with the Pleistocene ice age cycles. Pre-industrial levels of methane in the atmosphere were approximately 700 parts per billion, whereas levels exceeded 1867 parts per billion in late 2018. The net radiative forcing by anthropogenic methane emissions is approximately 0.5 watt per square meter, or roughly one-third the radiative forcing of carbon dioxide. Let's take a look at some of the lesser greenhouse gases. For example, surface level ozone. The next most significant greenhouse gas is surface or low level ozone. Surface ozone is a result of air pollution. It must be distinguished from naturally occurring stratospheric ozone, which has a very different role in the planetary radiation balance. The primary natural source of surface ozone is the subsidence of stratospheric ozone from the upper atmosphere. In contrast, the primary anthropogenic source of surface ozone is photochemical reactions involving the atmospheric pollutant carbon monoxide, or CO. The best estimates of the natural concentration of surface ozone are 10 ppb, and the net radiative forcing due to anthropogenic emissions of surface ozone is approximately 0.35 watt per square meter. Ozone concentrations can rise to unhealthy levels, that is, conditions where concentrations meet or exceed 70 ppb for 8 hours or longer, in cities prone to photochemical smog. The next lesser greenhouse gas is nitrous oxides and fluorinated gases. Additional trace gases produced by industrial activity that have greenhouse properties include nitrous oxide and fluorinated gases, or halocarbons. The latter including CFCs, sulfur hexafluoride, hydrofluorocarbons, and perfluorocarbons. Nitrous oxide, or N2O, is responsible for 0.16 watt per square meter radiative forcing, while fluorinated gases are collectively responsible for 0.34 watt per square meter. Nitrous oxides have small background concentrations due to natural biological reaction in soil and water, whereas the fluorinated gases owe their existence almost entirely to industrial sources. Let's listen from the Weather Channel regarding the greenhouse gases and how they play a role in the atmosphere today.
Throughout the atmosphere we have greenhouse gases. Some occur because of what we do. Some are natural, right? So we're going to give you an explanation of how this all works and what our atmosphere is composed of and what the net result is as far as temperatures go. So take a look at the map on the floor here, and what you're going to end up seeing are opportunities for us to show you how many different gases there are in the atmosphere, including stuff like water vapor, which can be a greenhouse gas, carbon dioxide, methane is a big one. This is captured underneath Arctic ice a lot, all the way down to chlorofluorocarbons, which is something that we help emit in the atmosphere. But what's the net takeaway here? Really, if we didn't have all of these gases, our atmosphere would be a lot cooler. In fact, it'd be 2 degrees below zero. So we need them to live on this planet, right? But too much of a good thing can end up being an issue. We're seeing the results of that now. With the added greenhouse gases that we have, when you take a look at what that means, the absorption from the atmosphere, it means that the atmosphere is now going to begin to warm for us. And we've seen that over the past 150 to 100 years with man-made emissions that have gone into the atmosphere. Take a look at this. Greenhouse gas, average Earth temperature 57 degrees, and it goes up the more greenhouse gas emissions that we put into the atmosphere. So the net takeaway is what we do has a result of increasing temperature.
Let's learn some more about the greenhouse gases from NASA.
The Earth's atmosphere is a mixture of gases. Some are known as greenhouse gases. That's because they trap heat from the sun and warm the Earth. That's good, because without greenhouse gases, our planet would freeze, and life as most of us know it would be impossible. These greenhouse gases, mainly water vapor and carbon dioxide, naturally cycle between the land and atmosphere and ocean. And over the ages, these greenhouse gases have reached a delicate balance that results in temperatures that we like a lot. It's been that way for thousands of years, until the last 150 years. That's when people began burning fossil fuels. Those fossil fuels, coal, oil, natural gas, contain carbon that's been locked away from the natural cycle for eons. But when we burn them, that carbon joins with oxygen to make carbon dioxide that goes into the atmosphere. It throws the natural balance out of whack. The more carbon dioxide in the atmosphere, the more heat that is trapped, and the warmer it gets. And the warmer it gets, the more the climate changes, and the higher the ocean will rise. The more we learn about carbon dioxide and other greenhouse gases, the better we can deal with the changes caused by global warming, because good planets are hard to find.
Thank you very much for listening to this discussion on greenhouse gases. For more such discussions, get the UPSC Practice app from the App Store.